So today we're going to finish up the partition function discussion for molecules. So in the past we've done translational motion in the partition function. We did rotational partition function, and today we're doing vibration and electronic together. So yesterday we did translation and rotation together. So today is two more. But the electronic is super easy, and we'll see that it really doesn't play into partition function because the electronic spacing of energy levels is so high. So today we'll see how vibrational motion is probably the most interesting motion thermodynamically for material science. So let's jump in. The vibrational motion is essentially the model that we use as the harmonic oscillator. So remember from last semester about these different levels. It's an equal ladder of states, meaning that the energy level spacing is equal, and that's different than, say, rotational energy levels. They went up as J squared. Remember, it was B times J plus 1, so it was a squared dependence upon J. The translational energy levels was N squared, but the spacing was so small or so close together that it was irrelevant. We just had 10 to the 30 levels filled at room temperature for, say, argon at 1 atmosphere. And so this is the default assumption for the vibrational partition function, even though it does fail in certain areas. So this equal spacing of energy levels is only applicable if you have a true parabola, right? The Hooke's law, and if it goes up to infinity. But if that thing doesn't go up to infinity, you have anharmonic effects, like a bond dissociation. So that's not a parabola. It starts to break and bend over. And so for bond dissociation or for internal rotation, like the rotation around the carbon-carbon bond in ethane. So that potential doesn't go up forever either. It turns over and you have 3 minima on that vibrational potential. Also for big masses and weak bonds, you have bond dissociation, and so you have anharmonicity. But for our purposes, we're just going to use the harmonic oscillator equation because it gets us 90% of the way there. So let's focus in on this energy equation and the vibrational partition function. You know, the first question, though, is where do we locate zero energy? And so we could locate it at V equals 0, and so that's that lowest vibrational state. But that's also a property of the molecule. And if we were to compare two different molecules, we can easily calculate the electronic energy minimum, which gives us the minimum of that parabola. And so we could also locate it at the bottom of that potential well. So you'll see in Gaussian 2 results for the vibrational partition function. One that has BOT in parentheses, and if it says BOT in parentheses in Gaussian, that means bottom of the potential well. It's setting 0 down at the bottom of the harmonic oscillator potential. And if you have 0 or V equals 0 labeled in the vibrational section of Gaussian, then it's setting that first vibrational state as the 0. It calculates it both ways. I just want to point that out to you in case in the future you need to use that. You'll remember, oh, we talked about that in PChem, and you can come back to the video. Okay. But the main thing is, where do you put 0? Because that's going to change how many energy levels are populated, right? And so for the most part, we just set it at V equals 0. But occasionally, there's rare cases where you need to set it at the minimum of the potential surface. The partition function is just the sum of the Boltzmann factors for the populations of all those levels. And so this is an infinite sum because you can go up to infinite energy levels. So it's e to the minus 0 plus the energy e to the E1, E2, E3. But notice that since it's an equal ladder of states, E2 is just 2 times E1. And so you can look at this, you see that it starts at 0, you have E1. E2 is just 2 times E1. And E3 is just 3 times E1. So everything is written in terms of E1, the base vibrational frequency. Yes?
Is that what one of those extra problems we gave us was looking at? Because it was like, first one was 0, then it was KT, and then 2 KT?
Yes. Yeah. So I think, give me more information about the problem.
We altered the first problem, which was like 0, 100, and 500 as a level.
Okay.
And it changed down to that.
I said yes right away because it was 0 KT and 2 KT, which is following this kind of pattern. But
it mainly was just like asking for the normalization constant, and then asked like would your answer change if there are 5 states in each state.
No, it sounds like it's a little different.
Okay.
Yeah. I'm pointing out that this is just multiples of the ground state energy difference because what this ends up being is it's kind of like a progression of squares, right? It's going up in higher power. So from x squared, x cubed, so e to the 0, e to the 1, e to the 2, e to the 3. That's a well-known series. So if you have this series, you see that it's just going up in integers in the exponent. And so that's very similar to this infinite series. Do y'all see that? You see e to the 0 is 1, and then this is, if this unit is corresponding to e to the 1, then you have e to the 2 here, and e to the 3 here. You see it follows this same pattern, and this infinite series converges, so that sum ends up being this. So in this case, what is x? X is e to the minus e1 over kt. And so then you get the partition function. So that infinite series, we actually were able to just count up to infinity. This infinite series converges. So we didn't have to do the integration on this one. This actual series converges to that pattern of 1 over 1 minus e to the minus hc nu over kt. Where this epsilon 1 here, it's right here, is this piece right here. That is the energy of vibration. So you have the vibrational frequency, and when we write it with the tilde on top, that's the frequency in wave numbers. And so then you take that wave numbers and you multiply it by the speed of light in centimeters per second, and then multiply by Planck's constant, which is joules times seconds. So that's per second, and the second cancel, and you end up with joules. So that's how you're converting the wave number value into joules. You don't have to do the HC part if you've already then divided Boltzmann constant by HC and have Boltzmann's constant in wave numbers per Kelvin. So if you're using the Boltzmann constant already converted to wave numbers, then you just put the vibrational frequency in there. Well, we'll see in another couple of slides, you can take the vibrational frequency and just go ahead and divide by Boltzmann's constant and the speed of light and Planck's constant and write the frequency in terms of temperature. And so you would call it the vibrational temperature. And then you can just put vibrational temperature on the top and the temperature on the bottom, and you have this ratio. Yes. So again, most of the time you do confusing things on the equations. You look at that and you go, this doesn't make sense. But it's all about the units. So if you just follow the units, then it'll make sense. You have a question? Okay. Yeah. Let me just check one thing. And so this vibrational partition function here is, let's compare it or kind of get a visual for what it's telling us. Okay, so if we take this vibrational partition function and we think about these energy levels, these vibrational energy levels shown over here on the right, the Boltzmann distribution tells us the probabilities of the populations of each of these states. And so I just wanted to spend a little bit of time on this curve here. So the probability of populating each individual energy level is shown in blue. And this may be a little confusing, but this numbers here, the difference between these different columns, is beta times E. So it's essentially E over KT. So it's just this piece, HC nu over KT. So that's what's being shown with these 4 numbers here. And so in this case, it's saying that HC nu divided by KT is 3.0. So that means that the energy spacing divided by the temperature is the energy spacing is 3 times the temperature. So this little orange bar I've drawn in here to kind of show you the thermal energy available. So KT is that orange bar. And the energy spacing is about 3 times higher. And so you don't have enough energy. Theoretically, you look at it and go, well, I don't have enough energy to excite any molecules. But there's a small probability that some of the molecules are in that first excited state. And so the blue bars show you where the molecules are. Most of them are in the ground state. A few are in the first excited state. Okay? And so that gives us a partition function in the blue piece of 1.05. So you see it's just slightly more than one level is populated. So about a 5% chance of being in the upper state. And then now the energy level spacing is equal to the thermal energy. So I kind of think of this KT as sort of the level of the thermal bath, right? So as you raise the temperature, the energy available in the room grows. And so now we have enough energy that matches the first vibrational state. And so we have many more molecules that are populated. In fact, the Q, the partition function, is sort of a count of the levels that are probably populated. And it's 1.58. 1.58. So that means we've got some molecules in the first excited state, but we even have a few in the second and a very few in the third. But we've got 4 levels that have a countable number of molecules in them. The next one now is 0.7, and so the thermal bath has risen. Now the energy spacing is 0.7 of the thermal energy. So that fraction is 0.7. Hc nu divided by KT is 0.7. So that means the top, if the bottom is 1, the top is 0.7. So that just means the temperature's risen. So now we have more thermal energy available, and so then we have more excitation. And then this last one, the vibrational frequency is about 1/3 of the amount of energy needed and available. And so the thermal bath has risen up to this high, this level, and just look at how just adding a little bit of temperature really drives the molecules into the excited states. We have molecules that are very excited here, and yet this would be our average thermal energy. So you see the vibrational population varies dramatically with temperature. And so that has probably the number one or the largest effect on the behavior of materials. And you think about, well, let's just think about this. What states of matter, and let's do a think, pair, share, okay? So pair up with folks nearby, okay? And you can do groups of 3 if people are far away. So y'all pair up and think about this. Think about the states of matter and the partition functions. And let's focus on the vibrational partition function. Which state of matter would it affect the most and why? So y'all talk about it amongst yourselves for a second, because I want you to really, when you bend them, is that they're vibrationally excited. And so they definitely keep their nearest neighbors at bay a little bit, because there's motion in those molecules. It's not enough to completely slip by like in a liquid state, but it's enough to give some flexibility to the polymer. But if you start to cool it down, then those hydrogen atoms and so on get a bit entangled. They're too close to slip past each other. And so you get kind of in a crystalline or amorphous glassy state, and then it becomes brittle and it can break. And all it takes is a little bit of temperature, and all of a sudden you've activated those vibrational modes, and now the material can flex. So it's really dependent upon the various vibrational levels in that material, and small changes in temperature can have a huge effect. So I think that's really interesting. And, interesting is, I guess, it's like beauty's in the eye of the beholder. Interesting things are in the eye of the beholder. Maybe you're more interested in gases or liquids, but I think for vibrational partition function, polymers and those kinds of materials are intimately related. And when we get to heat capacity, we'll see how the vibrational levels are the ones that are the most unknown in terms of a material's heat capacity. Here's just that equation plotted out. Notice it's essentially linear in temperature. and then it goes down towards 0, but then right at 0 it curves and hits 1. Okay, as the partition function should do. It should go down and then at 0 temperature go to 1, because 1 energy level is populated. And so looking at this, can we understand the various nature of this as t goes to 0? Okay, as t goes to 0. And so this is a skill I need you to know how to do, is say, describe how this equation goes to 1 when t goes to 0. So t goes to 0, that means this thing blows up, okay? If this goes to infinity, then it's e to the minus infinity, which goes to 0. And so it's 1 minus 0 on the bottom, so it's just 1 over 1. So you should be able to read an equation like a paragraph. Okay, what about as temperature goes to infinity? So as the temperature goes to infinity, then this fraction, if you have infinity in the bottom, goes to 0. And then e to the minus that goes to 1. And so then this is approaching 1 minus 1 in the denominator, which means q goes to infinity. So these are the skills. And when I ask you to describe the temperature dependence of the vibrational partition function, this is what I'm looking for. You can just walk me through with 4 little statements and say, this is what it's going to do. Now I know what q is going to do when temperature goes to infinity and what q is going to do when temperature goes to 0. And so this little theta is the vibrational temperature. So that's the temperature of the room, or the thermal energy divided by the vibrational temperature. And so we could take that substitution, take hc nu over k out and just put in a theta v. And so that shows up on the next slide here. So this partition function at very high temperatures just essentially goes to a linear equation of T over theta v, where theta v is the vibrational temperature. Now this is going to be only for a particular vibrational motion. And we know there are 3n minus 6 vibrational motions in a molecule. So the CH stretch is probably never going to be activated. Never going to be just temperature over vibrational frequency. But the big bending modes in a molecule, like naphthalene bending like a board, that's moving a lot of mass and a very small spring constant. So that's going to be a very low frequency motion, and it's going to be a very low vibrational temperature. So the total partition function is the product of all of the 3n minus 6 vibrational partition functions. So a molecule like water has 3 different vibrational modes, and so it would be all 3 of those multiplied by each other. I put this in red because it's important. When temperature is greater than 10 times the vibrational temperature, then we say that vibrational mode is active or activated. That just means a substantial number of molecules are in the excited states on that vibrational motion. And so this vibrational temperature, just to review, that's that equation, hc nu over k. Now with 0 point energy, if we put that energy level of we define 0 as the bottom of the potential energy term, then this is the partition function for, when I say with 0 point energy, we're just defining 0 as the bottom of the potential well, not the v equals 0 state. So let's look at Gaussian. Again, I did this calculation on this asymmetric molecule just to show earlier the rotational temperatures and rotational partition function. Now we have the vibrational temperatures. So here are the vibrational temperatures in Kelvin. So we have 3 vibrational modes. What do you think is the highest vibrational frequency in this molecule? The highest vibrational frequency. So we're talking about something that has a highest force constant. So that means it's going to be a stretching mode. And we need something with the lowest mass that's moving. Yeah, it'd be the H stretch, whatever the H is bonded to. So this is an OH stretch. That's the highest frequency vibration. So that's going to be the highest vibrational temperature. So that's what this one is, 5,800 Kelvin is the vibrational temperature of that OH stretch. So it would have to be heated up to 58,000 Kelvin for that to be active, for that to be in the excited states. Okay, that's not going to happen. This molecule wouldn't survive that temperature. Okay, the next of the three vibrational modes we have in this molecule, what's the next one? Probably the OCl stretch, because it's a covalent bond, and so even though the chlorine's heavy, it's going to be a stretching mode, which is probably, you know, makes it higher than the bending mode. The bending mode would be the hydrogen oxygen chlorine angle, but the hydrogen's pretty light, so I don't know. I'd have to maybe go look at the animation to see which one of these is higher frequency than the other. But anyway, it's one of these, and neither one of those would really be activated at reasonable temperatures. We'd have to go to 12,000 Kelvin to activate the lowest one, and to 20,000 Kelvin to activate the middle one. So the vibrations of this molecule, being such a small molecule, are probably not going to give it any interesting character. So it's going to be a gas phase molecule or in the liquid phase, and the vibrational partition function for this molecule will be very boring. It would just be 1. And so it would just be 1 for each of those vibrational modes. It's not going to add anything interesting to the partition function. It's not going to provide anything interesting to its heat capacity. Only translation and rotation are interesting in this molecule. It's the only ones that are substantially populated. So let's talk about our total degrees of freedom with a little bit of review. Okay, so how many degrees of freedom does this molecule possess? How many total degrees of freedom?
Oh, 3 minus, yes.
Total degrees of freedom. Y'all are close. You're bouncing around. It's just the 3n part. Yeah, 3n total degrees of freedom. That's everything it can do in terms of its motions. Yeah, 3 translations, x, y, and z. And then in blue, I have the 3 rotations. Those are your 3 rotational temperatures in green. And then in blue, I have the 3n minus 6 vibrational. And so we have 9 minus 6 gives 3. So here's the vibrational motion. So we've got all of the motions in the molecule. So here's the partition functions that we get from Gaussian. So it calculates them for us. It's very nice. We have the rotation, translation, electronic, which we'll talk about next, and then the vibration with V equals 0, the vibration with the bottom of the potential well set at 0, and then the totals. And we could calculate these. Okay. Let's just look at them. This is old school scientific notation in Fortran that Gaussian was programmed in starting in the late 60s. Okay, instead of times 10 to the, it's just d plus 4, d plus 11. Now in Excel, it doesn't understand d, but it does understand e. So if you were just replace those d's with e's, these numbers would go right into Excel. Let's just go ahead and break out their, put them in numerical format, get rid of scientific notation. So the rotational partition function is 2,228. The translational, it comes in at 14 million levels populated. The electronic is 1, and the vibration with V equals 0 is 1. Okay. Now, how can you explain this with it at the bottom well being 0.000002? All right. In other words, 0.2 parts per million. Why is it so low with the bottom of the potential well being defined as 0?
The energy levels larger. And the bottom is 0.
If you set it at 0, it thinks that's the ground state. And so this would be the probability of having molecules in the V equals 0 level if 0 is down at the bottom of the potential well.
Okay.
Yeah, and so it's a really, I just don't want you to be confused by this bottom thing. This is only very weird situations when you would use that. And so you would use the V equals 0 one, because that's realistically as low as the molecules can go. They can't go down to the bottom. Right? The V equals 0 vibrational state is the lowest a molecule can get. I just have to include a discussion about that VOT definition because Gaussian's including it. And I don't want people to be confused. So I'm just showing you, don't use it. It gives you some crazy numbers.
So would that be 0 Kelvin, or are there other factors?
It can't get below V equals 0 even at 0 Kelvin. It's really weird. Yeah. So this 0 point energy is a function of confined particles. It's I guess an effect of the quantum nature of the system, where you get down and you've got a wave function, and the standing wave, if you think about a wave, you know, it's between its boundary conditions. It doesn't go all the way down to the bottom of the potential well. There's a point where it stops, and that's at v=0 level. Yeah, it's weird.
So why does it even give you that? It's not possible.
It's for comparing. It's for reaction. It's for comparing products and reactants. And so it's trying to set the v=0 at the electronic energy, not the vibrational energy. And so then you can add in that vibrational energy later.
So would that have to do with like the smaller particles involved with atoms, like quarks and whatnot?
I don't think so. No, I think it's just the solution to the harmonic oscillator problem that gives you this v=0. We see it also we see 0-point energy in a particle in a box too, if you remember. I mean, no, we don't. Was it that or was it rotation? One of the other systems gave us 0-point energy as well, but the vibration does. It comes down to v=0, and then it essentially stops. It doesn't have 0 energy. We define v=0 as 0, but the potential energy surface is below that. And so let's look at these numbers to see if the total works out. So here's the total partition function. And obviously it's not the sum, because I can't add these 4 numbers and get that. But if I multiply them by each other, I do get that number. And so this total is the product of 1 times 1 times 14 million times 2,000. And so where does most of the energy levels come from? Well, it's the 14 million translational states that are populated. But there's also 2,000 rotational states that are populated. But there's only one vibrational state at each vibrational motion that's populated. They're all in the v=0 state for the bend and for the COH stretch and for the OCL stretch. Now, which one of these is going to be most temperature dependent? Well, you can increase the temperature and change this from 14 million to maybe 16 million, and then from 2,000 to maybe 4,000. But this is the one that's really going to be temperature dependent. Now, I'd have to go to really high temperatures, but my point is that going from 1 to 2 is going to double these, and that's going to be a huge effect. Changing the vibrational partition function has an enormous effect, and it's really temperature dependent. So just changing a little bit of that vibrational motion can really change the number of energy levels. The electronic partition function, the thermal energy is much, much lower than the difference in electronic states. And so if you do this partition function as a sum, it's going to be e to the 0, because you're in the ground electronic state. And so it's just the degeneracy of that ground state. So most of the time we call it G0, the degeneracy of the ground state, or the highest occupied molecular orbital with all of the other molecular orbitals populated. That's the ground electronic configuration from an MO diagram. And there are situations when it might be 2 or 3, but most of the time it's just 1. Paired electrons and so on. But like in nitric oxide, we have an unpaired electron. It can be in the pi, like the pi bond in the XZ plane or the YZ plane. So there's 2 options, and so G0 would be 2 for nitric oxide. But in almost all the other molecules, it's just 1. So G is the degeneracy of each level, and so it's just the degeneracy of the ground state. Now, what's what temperature would you have to be at to populate, say, a 700 nanometer homolumo gap? You would have to get to 20,000 Kelvin. Yeah, so you're not going to get thermal population of those electronic energy states. Now, you do have in solid materials temperature dependent conductivity, right? Semiconductors, you get electron hole pairs that you warm it up, and all of a sudden now you have a conductive material. And that's because you're dealing in a solid, and this homolumo gap has decreased down to where it's accessible thermally. Okay, but we're really talking about single molecules here. We're not talking about large solids. But that homolumo gap, electronic excitation in a large material, large solid can be thermally excited. So let's put it all together. We have the translational piece, and this is what Gaussian's using to calculate that translational number. You have the mass of the molecule, K, T, so on, it's constant. You have the volume here, nRT over P. Then we have the rotation. We have the 3 rotational temperatures, which are the rotational constants converted to Kelvin, dividing by Planck's constant, and so on. The sigma is the symmetry number. So if you have a symmetric molecule like N2, then sigma is 2. For benzene, think about benzene. You have inversion. You have all the different rotations and reflections. The symmetry number is 12 for benzene. I haven't figured out how they come up with the symmetry numbers. I have to look them up. Okay, so that's probably a question you have. How do you know that benzene's 12 and how do you know that N2 is 2? I've not come across a simple scheme that tells me how the symmetry number is calculated. It may be easy, I just haven't found it. And then we have the vibration. So we have the product of all of the different vibrational modes, and there's 3n minus 6 of those. So we have everything right here. We have the translation, rotation, and vibration for a molecule. And so we probably have time for one of these cahoots. Okay. So which one do you want to review? Choices, yeah. I looked at them last night. One of them was like 3 questions. One of them was like 5 questions. I can't remember which one. So. Yeah, that's right. We'll need to make a choice. Rotation it is. Okay. Oh, I gotta log in here. Let's see. Let's go back and click it again now that I'm logged in. Play. Okay, there's the code 652 oh wow, 652562. It's gonna screw me up. You want me to cut you out and you put back in or what? Okay. Yeah. What happened? Yeah, good. All right. Ready? Anyone trying to get in still? Okay, let's get started. 4 questions. We got lucky. Okay, which of these molecules has the smallest rotational constant? And all the equations are out there, so you shouldn't need to guess. This is the poles, right? It's either hydrogen or iodine, anything in the middle. Yeah. So it's iodine, mainly because of the mass, 127. Okay. So you can look at the equations here. So the mass here is at the moment of inertia, and then that's in the denominator. So the bigger the mass, the smaller the rotational constant. Okay. Okay. Rotational temperature. Now that equation is not shown on there. That was at theta V or theta R, theta A, theta B, theta C. Who got it right? Yeah, someone. Way to go. So again, the rotational constant in wave numbers is going to be proportional to the rotational temperature. You're just dividing by the units and converting it. Mainly, you're dividing it by Boltzmann's constant. So the wave numbers goes away and temperature comes back up on top. So higher rotational constant would give you a higher rotational temperature. It's just like higher vibrational frequency would give you a higher vibrational temperature. That molecule we've been looking at is hypochlorous acid. So when I say a symmetric top, constants A is greater than B, which is equal to C. You see they're very, very close. 30 and then 0.7 and 0.7. Why would it be that way? It's not a symmetric molecule. So this is a thinking question. Spread all the way across. Okay, if you look at the molecule, it's very similar to just the diatomic. That little hydrogen, I mean, oxygen is 16, and it's got this little hydrogen of 1 spinning around it. So it's very similar to an OH and a Cl diatomic. So it has two very small moments of inertia and then one very big one. Okay, what motion corresponds to the large rotational constant in HOCl? Think about rotational constant. Equations that we had earlier. So if something's heavy and moving, like iodine had the smallest rotational constant. What's that?
Did someone pick green?
Yeah. No way to know. Sure. So there's only 3 rotations, and so I had to pick 3, and I had 4 answers. So what am I going to do? Yeah. Very good. Yeah. So the hydrogen spinning around at OCl axis is a very, very small mass, and so that's a very small moment of inertia, which means a big rotational constant. So that's the one that's 30, and then B and C are equal to each other. Those are the tumbling of the molecules. So just a little review of rotational motion. Okay. Good job. Good job.
Yeah.